Hello and welcome to today's PSU Transportation Seminar. My name is Jason Anderson and I will be introducing and moderating today's seminar. Our PSU Transportation Seminars have been a tradition since the year 2000. These seminars are once again being held live on Portland State University's urban campus, located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, and Watlala bands of the Chinook, the Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. It is important to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, remember these communities, and to honor their legacy, lives, and descendants. Today, we are pleased to have Diane Moug. I had a 50-50 chance there. Presenting on geotechnical reconnaissance following the 2023 Türkiye, Syria earthquakes. Diane Moug is an assistant professor in the Civil and Environmental Engineering Department at Portland State University. She joined the department in 2017 after earning her PhD from the University of California at Davis. Her research focuses on how to improve in situ testing for characterization of geotechnical soil properties and engineering behavior. Her research has a particular focus on improving geotechnical engineering methods with the cone penetration test for characterizing earthquake behavior of soils and characterizing non-standard soil types. Her work has included studies of, I'm going to butcher this word, diatomaceous.
Diatomaceous.
That was close. In Oregon, soils treated with microbially, I butchered that one too. Introduced to saturation in intermediate soils. Here's a preview of our upcoming seminars. And as an overview of today's seminar, you can expect our speaker to present for about 40 minutes, followed by a Q&A session. We will be receiving questions through the Q&A feature on your control panel, and we'll ask them at the end of the presentation. If we run out of time, all your questions, we will give our speaker the opportunity to email written responses for any questions that were left unanswered. We have enabled closed captioning, but you must click on the CC feature on your control panel to view them. We will be recording today's webinar. It will be available on our website later today, along with the presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. With that, and butchering many words that Diane will pronounce properly, I'll hand it over now to Diane.
I'm just gonna have to try to pronounce it. Kurdish words that I'm butchering. Thank you, Becca. Yeah. Thanks, Jason. Okay, so put together this presentation kind of motivated by the seminar of we need a seminar speaker on Friday. So I thought I went to Turkey back in March to do reconnaissance following these earthquakes. And we did look at a lot of transportation infrastructure and a lot of issues that do focus or that do impact mobility of people and goods following an extreme event like this, like an earthquake. So I thought I could focus on and bring some of those observations together today. So mostly my focus is on the geotechnical features and then trying to tie them to how they impacted mobility and transportation. So a little background on these events. It was February 6, 2023, that there was a magnitude 7.8 earthquake that struck right here in southeastern Turkey. And then only 9 hours later was a magnitude 7.5 earthquake that struck fairly close by. And this is the regional tectonic setting of Turkey. So this is Turkey here, Syria down here, and Israel, Palestine down here. And so what we see is we have this tectonic plate, the Anatolian block here, and then the African plate and the Arabian plate both pushing up on the Anatolian block. And as my geologist colleague described to me yesterday, it's like a pea being squished between your fingers, where Turkey and the Anatolian block is that pea, and it's just getting squished. And as a result, we have high seismicity, a lot of earthquakes that occur in Turkey. So with these earthquake events, like I said, magnitude 7.8 and then 7.5 9 hours later, and then in addition to that, numerous aftershocks. On here, I'm showing the faults that ruptured and where they are in the context of Turkey, which is outlined here. And one thing, seismology is not my background, but one of the big takeaways that I've garnered from reading and listening to presentations on this is that this is very much an unprecedented event. It's called, some folks consider this a main shock and an aftershock, but really it's two major earthquakes that occurred very close to each other. And we just generally don't engineer for this kind of event. It is very unprecedented. So this is a look at a nice illustration. Oh no, I forgot to put the attribution on this. I will follow up and include the attribution of this. I'm sorry about that. But animation showing the ruptures as they occurred, which to me is just interesting to see that the way that these faults do rupture and that the seismic waves do propagate out from it. So when a rupture occurs, the first rupture, the 7.8 event, started here and then propagated in either direction, north and south. And then the second event on this fault up here and propagated kind of east to west. I'm not going to get into it today, but the direction of propagation along these faults does affect the seismic response. So that is something that kind of becomes considered when evaluating earthquake hazards is what is the different rupture scenarios that we can have. If we know that there's a fault and the type of fault, where is that rupture going to initiate, and then how is it going to propagate? These plots here, I took from the USGS, and they show the peak ground acceleration, so the intensity of shaking that was felt from these two events. This is from the first event, the magnitude 7.8. The red contours show where the peak ground acceleration, the shaking was strongest. So we can see that it extends over quite a large part of Turkey, from south in Antakya and Iskenderun, which I'll be talking about, and then up north as well. And then this is the second event, which was more centered around Kahramanmaras and in the north part of Turkey. But the bottom line is that there were some areas that just had one strong shaking event, and there were some areas that had two very strong shaking events. So I have to touch on just the extent of loss of life and damage that occurred from these earthquakes. It's just under 60,000 people in total that died from both in Turkey and Syria. I took those values from Wikipedia, so I don't know how vetted they are, but it seems to be sort of in line with the way that the numbers were marching up in the days and weeks following the events. There were widespread ground failures, liquefaction impacting structures, bridges, lifelines, ports, and dams. And I'll be touching on a little bit of this, but we saw on those maps the large extent where the severe shaking took place. And so damage was spread throughout Turkey and Syria. I'll get into the Reconnaissance in Syria. And then many collapsed in heavily damaged buildings. From the GEER, the Reconnaissance reports following these events, over 35,000 collapsed and partial collapsed structures, with almost 180,000 that were heavily damaged. So the reconnaissance efforts that I was a part of, it's part of a group called the Geotechnical Extreme Events Reconnaissance Association, GEER, and they were in partnership with researchers at Middle Eastern Technical University and the Earthquake Engineering Research Institute. So GEER focuses on the geology and the geotechnical aspects. EERI encompasses, they do a more comprehensive effort looking at impacts to hospitals, to lifelines, transportation structures. And they do a very nice job of pulling together all the different disciplines into understanding kind of the full effect of these earthquakes and the full impact of these earthquakes. So GEER sent 3 teams in the days and months following the earthquake. First team is a small team that goes within the first about week after the major response has happened, and they're there to kind of get a big overview of what's happened, and then send in the second team that can do more detailed measurements. And then we were part of the third team, which can again pick up even more detailed measurements. The idea is, and the goal is to collect perishable data on ground failure, infrastructure performance, fault rupture, that will create case studies for engineering that really are the basis of our engineering practice, is to be able to learn from these events and have case studies to inform our future practice and design. So we need to get there fast when it is safe to do so, when we're not impeding emergency response efforts, and to collect these data. The focus for the most part is on impacts to infrastructure. There's lots of interesting cases where you can look and see that there was slope failure, ground failure, and those have value. But if it's not impacting infrastructure, then there's not as much to learn from it. So the goal, at least as I'll be presenting today, is the impacts to infrastructure. And then finally, why Turkey? Turkey is a very seismically active country with a lot of history of earthquakes, and they have a fairly good understanding of their seismic risk and also seismic code and standards that are similar to the US's. So if we are able to study what's happened in Turkey, then we can also apply those lessons learned here to the US. Reconnaissance wasn't done in Syria just because of the instability of the country, of course, but there is some study that's going on based on kind of remote sensing or imaging where we can learn about the impacts of Syria. So yes, this is our team made up of 4 folks from UC Berkeley, Ohio State University, and Sena, who is from Zeytaş Engineering in Istanbul. And we focus on 3 areas. There's Iskenderun, where we spent about 3 days down on the Mediterranean Sea. Antakya, down south, which this city was covered quite a bit because there was just a lot of structural destruction in the city. It was quite widespread and quite impacted. And then up north in Gulbashi, where there was a lot of liquefaction and a lot of interesting things that we can learn from that city as well. So what I want to do today with this presentation, I want to be able to provide some observations of geotechnical transportation and seismic interactions that we observed. This was just a few months ago. We're still processing and learning lessons from these earthquakes. So these, for the most part, are very preliminary. And we're also planning to go back to collect more data from the subsurface that you can't really collect when you're just there with a week's notice and trying to gather as much perishable data as possible. We plan to go back to collect data that isn't at as high a risk of losing, but is still very valuable for understanding what happened during these earthquakes. I also want to highlight some novel geotechnical earthquake observations, some things that we haven't seen or that we rarely see. And then also relate these back to how we can think about earthquake risk and earthquake planning in the US and particular in the Pacific Northwest, some parallels that I see between Portland and what we saw in Turkey. So starting with transportation infrastructure. Overall, the general takeaway from this earthquake was that transportation infrastructure did perform fairly well. There were some bridges that were damaged and severely damaged. The ERI team surveyed 2 collapsed bridges, 8 bridges with severe damage, and 13 with moderate damage, but 75 that had light to no damage. And in several of these cases, I think with moderate damage, the bridges could be up and operational again with a little bit of response. There were some roadways that were damaged from geotechnical issues. And then our team, we also surveyed 4 bridges and an underpass, and I'll get into those since I have the details on them. So I chose to highlight starting off with 2 bridges near Antakya, one that remained operational in the days following the earthquake and one that was closed. So we can just compare their performances. So this is the operational bridge, fairly major roadway in Antakya into Antakya, and a twin bridge here. They seem to have similar design and construction between these 2 bridges. This is the survey that we did at the bridges and various measurements that is kind of a lot to absorb right now, and I don't expect you to, but I'll highlight some things from this bridge. This is an image from Google Earth. What we do see is that at the abutments onto the main deck of the bridge, there is road patching that took place. It is quite common to see, and I'll show several examples of this from different bridges, but that the approach abutment will settle during the earthquake, making it so that vehicles can't move across the bridge. And so if there's a quick response of patching, then that bridge becomes operational, if that is one of the only issues, or all the other issues remain minor for the bridge. With this bridge, we also saw that there was compression of the deck and the abutment moving into the deck. It remained fairly minor, and as you see, this bridge is operational. We saw that there were slope failures. We're talking about geotechnical engineering. We saw slope failures both to the east and west of this abutment on either side of it. And we can see that slope that's moved and failed on either side, which puts force onto the abutment and causes part of that rotation and compression of the abutment and bridge deck. There was deck expansion and shafts with spalling. So these are the shafts, part of the foundation of those abutments. We saw damage and concrete spalling at them. And then also just some more compression and tilting abutment and deck. So, but overall, this bridge did appear to perform fairly well and was operational in the days since. This is the second bridge that we went to fairly close by, so a similar seismic demand at this bridge. This bridge is the one that was closed. Also a twin bridge on the other side, similar construction and design. And what I'll point out here is that it was very close to the stadium in Antakya. And this stadium, you can see in the parking lot here, this was taken in the days following the earthquake. It became an emergency response base and a place to house displaced people. And so having this bridge closed and not operational did, at least from my perspective, it was an issue for moving people and goods in and out of the stadium. There became quite a long route around that they had to go to get there. And then you also saw people that were just crossing barriers and saying, no, it's just faster for me to go across this closed bridge. I'd rather do that. So there are still these impacts to people and movement that we saw in the days since. So surveying happening at the bridge as well. Like I said, it was closed. And we did see the structural issues for it being closed. These appeared to be mostly structural, the reasons for closing the bridge. The geotech impacts didn't seem severe. It just seemed like the bridge was shaken very hard and that it wasn't able to withstand that shaking. You see the structural elements here that failed. The struts across the bridge, we can see that they were compromised and the structural components were compromised on the bridge. And then there's also bearing pads beneath these struts that they sit on between the abutment and the strut. And those during the shaking, a lot of them seem to be displaced and had just in some cases been just spit out of the bridge and were on the ground. So it was just concrete on concrete. There were some geotechnical issues at this bridge where we did see again some slope failure along the river. You can see the leaning transmission towers in the background indicating that the slope did displace and had rotation. And then just at the bridge, there were just other things that we surveyed, like a drop between the deck and the abutment and a gap between them. You can see the displacement and the offset here. All right, okay, another bridge in Antakya, within central Antakya, and this, I think that this Google Earth photo was about a month or so after the earthquake, but you can see the amount of destruction that happened in Antakya. It's pretty incredible. And it looks like a lot of the demolition had occurred at this point, but all of those empty lots of our buildings once stood. This bridge, it does show us where there were some geotechnical issues around the bridge that at this point, I can't say whether they did contribute to the bridge's poor performance. And actually, I think that I can say that there are some, but we do see these geotechnical failures that are then impacting transportation infrastructure. So major ones at this bridge that were obvious were failure of the retaining walls on either side of the bridge that weren't able to withstand the seismic load and we get the failure of those retaining walls. The bridge, I don't know if you can quite make it out in these photos. It's kind of like obvious once you see it, but there was compression at this bridge. So you can kind of see this utility pipe here is where you, if you squint, you can see it, that it is in compression and you can see a bend in that utility pipe. So there was movement on either side of the bank inwards, compressing that bridge. Again, the drop between the abutment and the deck, where if everything else is performing well and then this happens, you are not getting vehicles across the bridge. And you can see that there's almost like a makeshift approach developed here in a lot of cases. And interestingly, we did see these kind of efforts undertaken where there was collapsed building and rubble that cover a road. And folks just kind of create their own road across that rubble. This is another bridge that actually we didn't survey. We didn't go to this bridge. It was too close to the Syria border for US citizens or permanent residents to get close to. But a contact I have at the Canadian Reconnaissance team, they did go survey this bridge. And this bridge is a case where it looks like geotechnical failures can be tied to the performance of the bridge. I'm going to explain what liquefaction is in a moment, but just these sand boils here are an indication that liquefaction took place and that it is a contributing factor to the performance of the bridge. So what we see here, this pile in the background, you can see that it's been tilted and tilted, that it's been twisted and tilted. And then there were slope failures from liquefaction on the approach or the banks of the approach of the bridge, which again appeared to fail the bridge. With these bridges, as I understand it, this bridge was closed and then this bridge was operational, the twin bridges. A case where similar seismic demand between them, but very different performances. Yeah, so and then this is another picture of the bridge where you can see, and you can kind of picture that the failed slope has moved into the bridge and caused all that force and loading that then failed it. And this is looking at the approach and the abutment, the tilting of it. So that's kind of what I have on bridges for the most part. I'm going to focus now on Iskenderun, where we did spend quite a bit of time and where we did see a lot of geotechnical liquefaction failure of the ground that then impacted buildings. But I did see a lot of connections to transportation within Iskenderun too. So down here in the south, on the Mediterranean Sea, or the Bay of Iskenderun, I think it is. And Iskenderun is Turkey's second largest port, so a significant city to be able to move people and goods. What we saw in Iskenderun, widespread liquefaction, lateral spreading. Like I promised, I will discuss liquefaction in a moment. It induced building settlement. We saw an increased flood hazard post-earthquake, many collapsed buildings, and damage at the port facility. And I'll discuss all of these. So what is liquefaction? When we have sand that is loose and saturated with water, during earthquake shaking, that sand wants to get denser. You think of like a jar of coffee beans, you want to fit more coffee beans in it, you shake that jar, those coffee beans settle, and now you can put more in there. Same thing happens with sand when we shake it in an earthquake. That sand wants to get denser. But earthquake shaking happens so quickly, and there's water in the way, so it can't get denser. You can't compress water. Water doesn't have time to flow out. So instead, those particles, instead of actually getting denser, they just end up suspended on the water. They're putting their weight on the water. So no longer do we have sand particles against each other, developing strength. Now they're just on water. Water does not have shear strength and it just flows. And our soil acts the same way. It flows and it acts like a liquid. It no longer has shear resistance. So during liquefaction and earthquake shaking, soil completely loses strength and stiffness. And I have a demonstration that I like to use. It's just a bucket of sand full of water. There's a brick on it, just like a building. Oops. And actually, I might need to trigger this. Yeah, so the hammer comes along. The hammer is the earthquake. And you can see in the bucket, you see water coming to the surface. You see that sand kind of acting like a liquid, and our brick building is settling and tilting. And it looks an awful lot like this building that has settled and tilted on a liquefied soil. This building is from, I believe, the Japan earthquake. I'll have to double check that, but it's actually my thesis or PhD advisor, Russ Moug. It's a photo from one of his past reconnaissance trips. So what do we see when we see liquefaction from an earthquake? We see sand boils and surface water. We see lateral spreading where soil loses its strength. So if it's on a slope or there's like a river nearby, it just flows out that way, or there's no longer resistance. The sand boils are because at depth, that sand or that soil becomes like a liquid and it wants to relieve pressure. It flows upwards, takes the sand with it. So this is a sign we often get that there was liquefaction in an area. And remember at that bridge down by the Syria border, there were sand boils. So evidence of liquefaction that occurred at that bridge. And we saw lateral spreading at that bridge impacting the structure. More examples of liquefaction from other earthquakes. I feel kind of silly including these slides because there's plenty of examples from this earthquake, but I hope that this just shows you that this is not an isolated phenomenon. Liquefaction happens during earthquakes, and it is something that we need to be concerned about here in Portland in the Pacific Northwest. These are from the 2011 Tohoku earthquake in Japan. You can see widespread liquefaction ejecta that occurred in this residential neighborhood, and you can see the tilted house in the background. This is showing a house that settled, or the ground that settled, I believe. It looks like this ground settled relative to this house. Bridge failures from liquefaction, there's several classic examples of it, from 1964 in Nagata or 1995 in the Kobe earthquake. And actually there's several from the 2008 Chile earthquake. There's several examples. So back to this earthquake, back to Iskenderun. I mentioned that Iskenderun is a port city. It was largely developed in the 20th century, where prior to that, it was still a port, but it was described as a very swampy city, like where it was difficult to settle, it was difficult to live because of just poor drainage in general. And as part of the development in the 20th century, they built drainage canals, drained the city, filled in that land, and then also started to build out the shoreline as well to really build up this port city. And this is, I just like to include this example to show that development. This is a building that we did survey during our reconnaissance here. I think it was built in 1930s or so. But anyways, you can kind of get a sense of the age of the building. Sitting here on a major boulevard in Iskenderun that runs close to the coast. And this is the same building back in 1960. Oh, I guess the building's older than 1932. Anyways, back before Iskenderun was really developed. And you can see that it's on the old shoreline of the city. So that shoreline has been built out and the land has been pushed out in Iskenderun. And this is an overview of the areas that we surveyed. But the takeaway from this, this figure is just in this hatched area, based on historic maps like this one, this hatched area all along here, that's our interpretation of where the land has been built out and where they've extended and put fill down for development. This is a survey photo or aerial photo from 1969, showing a little kind of the starts or where the coastline is today. And you start to see that there's been a little bit of building out in 1969 from that original shoreline as well. So building up has happened over time. Takeaway from this is just that Iskenderun, a large part of its development is building reclaimed land and fill. And so why I want to kind of impress on this reclaimed land is that in the red zone is where we saw a lot of liquefaction. And the symbols are where they saw liquefaction ejecta. So reclaimed land we'd see very poor performance for liquefaction on reclaimed land. And our observations in Iskenderun were consistent with that. We saw a lot of building settlement, a lot of liquefaction and ejecta. That's consistent with the historic shoreline and reclaimed land. Some examples of liquefaction and lateral spreading, we saw damage on sidewalks and roadways. These are pictures of still lateral spreading and damage to roadways, ejecta that covered large areas of land. These are photos, I believe actually that one of the first teams got from residents in the area. You can see ejecta that it was very widespread. It covered roads. It prevented mobility and response in the days following, or in the hours following, I would say, just with the amount of liquefaction ejecta that covered the roads. Then there's the port of Iskenderun. Like I said, second largest port in Turkey. There was quite a bit of damage at the port. There was ejecta and lateral spreading observed. So we do know that there was liquefaction that occurred at the port. The port did not function for a period due to misalignment of the cranes. And then there was also a very large fire that took place in some of those the cargo containers following the earthquake, and that was reported on by several news sources. You can see that on Google Earth as well. There was quite a bit of Google Earth imagery following the earthquake, and you can see when the fire started and by the time it had been extinguished as well. So ports are something that we do need to consider, at least from they're a geotechnical challenge for earthquake performance. There was also an underpass in the south part of Iskenderun. Actually go back here. So it was down here that in Google Earth, we saw that it had flooded in the days following the earthquake. You can see the water in the bottom of it. And our thought there is that liquefaction had occurred at depth. It didn't really impact things at the surface, but that relief and that buildup of water had relieved itself in this underpass, limiting transportation through the underpass due to that flooding as well. We did go survey it while we were there, and there wasn't any apparent damage to the underpass. It performed quite well. It was just this flood hazard in the day following the earthquake. What we did see is, and from talking to local residents, is that flooding is much more common in Iskenderun and happens much more frequently than it ever did before. This was March 29th when we were there, and there was flooding to several blocks back in some areas of the city and the main center. One of the main roadways is just here on the other side of these buildings. That's actually the community center that I pointed out a couple slides ago. And our thought here is that liquefaction took place in Iskenderun. There was such significant settlement from that liquefaction that now it's at a lower elevation regionally, and flood hazards are now, it's much more susceptible to flooding. So it's a really interesting kind of co-earthquake hazard that we're seeing due to this earthquake that's continuing in the days, months, and likely years following the earthquakes. We spent a lot of time looking at buildings. These don't apply directly to transportation, but I think they're very interesting. So we surveyed about 23 buildings in Iskenderun to understand and to measure their settlement. We saw settlements from 0 millimeters all the way to 740 millimeters, with a significant amount of liquefaction induced settlement in this area called the Chai district, which is almost entirely on reclaimed soil. Actually, I saw that some folks used to call it like the swamp for development. These 4 buildings were particularly interesting. What you see between them is that the ground has mounded between these buildings, where we are assuming that it used to be relatively flat, maybe with a little bit of a gradient out to the streets to allow for drainage. But we see this gap, or the mounding between them, and also in the ground tiles showing that there's extension that's taken place. You also see floodwaters that's pooled around those buildings, indicating that there has been settlement. We had a LiDAR device out there to take measurements of the ground in the buildings. And again, you can see with these LiDAR data that distinct pattern of the curving of the ground between these buildings. We had settlements at the buildings up to about 70 centimeters and in some about 25 centimeters. But the hypothesis here is that the buildings on either side, they settled and they seem to drag the ground down between those buildings. But you usually don't see, it hasn't been documented that there has been that significant building ground interaction from earthquakes. So this was actually something quite interesting to see. And yeah, this is sort of a schematic of what we expect to happen, that building settled and it dragged the ground down around. So, and because there's buildings on either side, we see kind of this bending or hogging deformation. And there's another set of buildings where we saw this, where these 2 buildings settled. This light steel frame building in the middle, the hookah bar, it didn't seem to be impacted directly by the liquefaction, but you can see the ground that's bent underneath the building due to settlement of those 2 adjacent buildings. And yeah, and then damage that occurred to this restaurant due to these adjacent buildings and the interactions. There's tensile cracks here in the retaining wall and in the roof side. And then in the slab foundation, you can see lateral cracks that run along the length of the slab floor. So even though this building, if it had just been standing alone, may have done fairly well in the earthquake, because of the presence or interactions from those adjacent buildings, it looks like we're seeing significant damage at the structure. Yeah. All right, so that was a Iskender. Now up to Golbashi, up in the north. So this in Golbashi, we spent a day there and we focused on building performance and liquefaction. There was a lot of fine-grained. So I described liquefaction as occurring in sands. It can also occur in silts, fine-grained soils, with a little bit of like clay plasticity to it as well. We don't understand these soils and their liquefaction performance quite as well, but we know that under certain conditions with certain properties, they are susceptible to liquefaction, and that we can see, even without liquefaction, significant damage. And then for geotechs in the room, we've measured the plasticity on the ejecta, and we see a plasticity between 8 and 14. So quite an interesting case that we have here. These are the buildings that we surveyed, just an overview of them. And actually we didn't, like on this page here, you see a building that punched, it looks like half a meter or so into the ground. We actually didn't focus so much on these buildings where we saw really significant settlements. We focused more on those where you just see like 20, 30 centimeters of settlement or less. Because one of the things that's just as important as understanding the failures is understanding what performed well and why. Yeah, and this is just an overview, like looking down a street in Golbashi, where you can see that it looks like not a single building is unaffected by the earthquake, and we see different degrees of performance. This apartment building here, so there's 2 apartment buildings, very similar setting, very close together. One building to the south had about 100 millimeters of settlement, maybe even less, depending on how it's analyzed. So it performed very well. People were living in this apartment building. It had a basement. And then we look across the other way, a building that did not perform as well. It had about 250 millimeters of settlement overall. 250 millimeters is considered significant, and no one was able to live in this building following the earthquake. So this one did not have a basement. So again, we see similar demands, seismic demands, similar age and construction between these buildings, but that difference in foundation conditions. One building could still house people following the earthquake, the other could not. And now I'm kind of just giving some last thoughts here. Another thing I want to point out, I'm now jumping down to Antakya, where we went to visit a hospital. And it's like this, I don't know much history of the hospital, relatively new. I think it was built following 2010. New hospital, lots of glass up on the hill, looks very modern. And it was shut down, this large hospital. And a lot of the emergency efforts were now happening in the parking lot following the earthquake. And I'm not too sure what structural components or what caused the hospital to be shut down. I don't know that information. But what we did see was that there were a number of things that should be fairly simple and that should perform well that can hinder emergency response following an earthquake. We saw entrances, ramps, stairs that had failed. And this is the emergency entrance, and we see the ground had differentially settled where you're not going to be able to get an ambulance to back up over that following an earthquake. And we also saw a settlement around utilities as well. So these are the things that as engineers, we can engineer fill, we can engineer entrances, and they shouldn't be afterthoughts. These have impacts. And like I was discussing with my geology colleague, there's concerns that following an earthquake, if this happens at a fire station or at a fire station, let's say, or other emergency response structures, you're not going to be able to get those vehicles out to respond. And so these kind of details, they do matter, and we do need to pay attention to them. So continued research following this, like I said, that influence of the buildings on the adjacent ground and adjacent buildings is quite interesting. What was it about this setting, this earthquake, that we are able to observe that where we haven't observed it in other settings? How to account for long-term co-seismic hazards like flooding that we see, that increased hazard due to flooding. And what areas are susceptible to this kind of flood hazard following an earthquake. And then also that fine-grained and plastic soils and the liquefaction in them that we saw in Golbashi, that's interesting for us as additional case studies and information that can be carried forward to our practice. So I sat down to think about how this relates to Portland and the Pacific Northwest. And my mind always goes back to the CEI hub, the Critical Energy Infrastructure Hub on the Willamette River. So this is where most of Oregon's fuel is either stored or handled. Fuel which we'll need following an earthquake to recover, and also which can spill into the river, which can ignite, and the community of Linton is just up here and be hazardous to those folks around. This area here, this land that's all flat along the river, this is all reclaimed land and fill for the most part. So understanding that we already know that there's a big hazard on reclaimed land for liquefaction and earthquakes, but we just felt like it's just a good reminder that the CEI hub is at significant risk to an earthquake here. Liquefaction and earthquake hazard of fine grain and plastic soils like we saw up north in Golbashi, lots of fine grain and plastic soils in the Pacific Northwest that we're concerned about. Aging infrastructure constructed before our awareness of seismic hazard. I think that we all know that this is important for us to be considering. Co-seismic hazards such as flooding and landslides, landsliding in the West Hills, blocking up transportation routes, flooding, blocking up transportation routes. And then emergency response impeded by liquefaction, ejecta, bridge abutment settlement, and then fill settlement outside of firehouses, hospitals, etc. So I want to leave off on this. If you want to learn more about earthquake response, the Earthquake Engineering Research Institute is a great organization. I was involved with it all through my graduate school, lots of opportunities for students. And for earthquake reconnaissance, they mobilize a virtual reconnaissance team that's gathering data from Twitter or news sources in the local area, and then that gets fed to the on-the-ground team so that they're directed where to go. So the virtual reconnaissance is a great opportunity for students to learn more. And then there's several earthquake hazard research projects happening at PSU that you can be involved in. Just acknowledging the team, the NSF funding and EERI as well that supported this reconnaissance. And staff, questions?
That was fantastic. Thank you, Diane. For those viewing the webinar, please feel free to submit your questions using the Q&A feature in the control panel on the bottom of your Zoom window. And we'll start with a question of anyone in person.
How readily available are like geomaps for the area or boring logs?
Not, yeah. So there might have been like a little bit of a, like I'm not able to Google things in Turkish, I guess. A lot of them are published in Turkish for Turkish people, right? So there might have been that challenge. We did try and find some geology maps and boring logs in the months since to add background. And we managed to get some through contacts, but it's still not that available.
I have a quick question for you. Having looked at the bridges that have been closed, how did the government, number one, communicate these bridge closures, and two, how do they enforce them?
You know, I don't know. I can't answer that. It would just be pure speculation. Yeah.
Oh, when they were looking at it, I could see like the tire tracks, like people had tried to transverse the bridge.
I think, yeah, as far as what we saw to indicate the bridges were closed, it was usually just like those orange barricades.
Okay.
Or like, yeah, I don't even know if it was concrete barricades. It was like, is the orange barricades filled with sand or something so that they don't move very easily? Yeah, something like that to indicate it was closed. But motorbikes, folks, could,
Pedestrians.
yeah,
bicycles.
could bypass and access.
Yeah, I'm just curious if you observed any impacts to rail infrastructure.
Well, that's a good question. I didn't. I think that there may have been some rail infrastructure impacts. I should say that the report, the EERI GEER report is available at the GEER website, and it does a very thorough job of documenting various impacts. That like the first folks were able to I think, fly a plane to get a like bird's eye view literally of what happened. And I think that there may have been some impacts to rail due to rupture of the faults that offset things. I want to say more up in this region here, you'd see misalignment of rail tracks. But yeah, I'll refer you to the report to get an idea of that. Elizabeth.
I noticed that when we were looking at the damage to bridges, that those are mostly concerns with what is happening along the shore, what's happening with soils near the bridge. But later, when you looked at buildings, you're talking about how the buildings affect one another. I was wondering if there is research into like those twin bridges on what the effects of one half of the bridge has on the other half. Like, do we know when we're building bridges side by side, what effect they will have?
It's a great question. I'm sure folks know. I don't. Yeah, I don't know about that, but that's a very interesting question.
I have a question. So I have a structural question and a transportation question. So I'll ask the former first. So you mentioned that the structural design codes are very similar for the US and for Turkey. What year, has that always been the case, or is that something that's more recent? And then part B of that question would be, do you know how much that they've gone through knowing that they're a high seismic area and retrofitted a lot of the structures and bridges like the Northwest has started to do in recent years?
Second part, I don't know. First part, I think that it was after the 1999 Coachella earthquake, and there's been a few earthquakes in the past that I think were quite destructive and really upped the seismic code, going along with our own understanding of earthquake engineering. And so I think that there's been a lot of construction in the past 20-25 years in Turkey, and I think that they, for the most part, are following modern seismic codes for this construction boom.
Yeah, we do have an online question, which is, while in Turkey, was there evidence of reconnaissance work by the local professionals there?
Oh yeah, so we worked with, it's a great question. We worked with folks from Middle Eastern Technical University. We were on the ground with them for a couple of days, and they were very involved with the previous teams as well. And then we were in contact with a professor from Iskandariye Technical University who had been involved with the previous team, who kind of gave us some guidance and has been helping us quite a bit, getting structural plans and boring logs, a lot of information since. So yeah, the Turks are very, very engaged in this. But what I will say is that other teams that were surveying lifelines, one thing that they noted was they had folks on their team that were going around with them from the area, but one of the big challenges following the earthquake that they observed is that people have had immediate losses within their own families in Turkey. And so they're expected to both respond to this earthquake and then deal with their own loss as well. So that's also another challenge that comes to emergency response.
So you talk about different infrastructure, especially different bridges perform rather differently, even when they are very close to each other. And then even a building, apartment building that are very similar, but on the other side of the street. So what are your hypotheses in terms of why such a difference in terms of that? And then maybe related to that, I think you alluded to when you talk about the hospital, is there may be kind of engineers when we construct the building, we can ensure that even the building may kind of still stand, but we can do a better job to make sure that the ground still holds during a major earthquake. Can you maybe elaborate a bit on that?
Yeah, so as far as the building performance, between these two apartment buildings, it came down to foundation conditions. Buildings with a basement do tend to perform better, just because you've excavated out soil, you now have a basement in its place. And so you no longer have 3 meters of soil that can liquefy and settle. Instead, you have a basement. So that's part of why at least these buildings appeared to have performed well. You can also do buildings on pile foundations that tend to do quite well in earthquakes. Yeah, here, these three buildings, quite tall, like most of these buildings are 5-6 story reinforced concrete buildings. These were like 10-12 story kind of buildings that were most likely on pile foundations, and they performed quite well. This building here, relatively little settlement for the district, 240 millimeters, whereas in others we're looking at more like 400, 500. This one was on timber pile foundation. We were able to speak with the building owner, business owner. So, and that one did perform quite well. So yeah, foundation condition. Yeah, I mean, you kind of you have to have it all, right? You have to have the right foundation, you have to have the right structure, and yeah, to have good building performance, you can't overlook one or the other. And then I think as far as like the entrances and fill settlement, that's just a matter of proper compaction. Like we as geotechs, we know how to compact soil, and so it's just not overlooking that and doing the proper engineering. One thing that was pointed out to me is that you often see that fill settlement right near like entrances and walls. And it's because it can be difficult to compact in those areas to get the machinery all the way out to the edge. And so, yeah, there's just addressing those difficulties and those challenges.
A related online question, somebody's wondering, what were the biggest differences for bridge failure? Age, design, material?
Pure speculation at this point, yeah. Yeah, I don't know. I mean, it could be a lot of things, like those bridges, even though they're close to each other, they were oriented differently. Like one may have been oriented like this and the other like this. And if shaking's happening in this direction, you're gonna have different demands on the bridge. So it's a lot of things.
At the beginning of the presentation, you started with saying that the overall transportation infrastructure performed pretty well. I'm wondering how the utilities perform, because oftentimes utilities are like incorporated into the street infrastructure. And I wonder how that works.
I can't say, I'm not sure. Yeah, I don't know. I'll refer you to the report. It may address that. Yeah, I'm not sure. I'm sorry, I can't answer that.
Another online question, somebody's wondering how developed the bicycling infrastructure is in Turkey, and if you saw any effects on or impacts to that.
I'm not sure. I don't know. I mean, a few people on bikes, but not that many overall.
So I have a transportation related one. I don't recall how quick it was after the earthquakes that you all went there for reconnaissance, but by the time that you got there, did your team experience any transportation related issues or observe any transportation related issues at that time?
That's a good question. Trying to retrace our steps. There may have been, so part of this is Sena, who was the Turkish member of our team, she did all the driving. And I was either in the back seat, like looking at notes or sleeping. And so there may have been detours and routes that she took that I just wasn't aware of. I feel like as we went from the south up to the north, we may have had to take a detour, but I'm not sure. Yeah, it's all a blur. I don't know.
In thinking about like the Northwest in relation to this, I was thinking a lot about like Seattle and the Denny regrade that happened like in the 1800s, and how a lot of the coastline of like the city of Seattle is on like a liquefaction kind of zone.
Yeah.
Like, in your opinion, should we not be building in those areas, or are there things that like engineers can do to make those buildings more stable? Like,
yeah, and so we can engineer it as long as we're aware and we respect those conditions and we do the right analysis to understand them. And then it does take more money, I think, is one of the big issues. Like at the CEI hub, we have somewhat of an understanding of the hazards, and it's just going to take ground improvement, and it's going to take retrofit, and it's all expensive and it takes money. But you can put things on piles, you can improve the ground, you can do soil slurry mixing to reduce the liquefaction hazard. Yeah, so we can build and we can engineer those areas. Yeah, but we just do need to respect the hazard.
Have they settled on a remediation effort for the CIN?
For the CEI hub? So I think that at this point, they just passed legislation that, each owner operator, each site needs to do a seismic hazard assessment or a seismic assessment. I'll encourage everyone to go look this, like double check what I'm about to say. And so the Department of Environmental Quality, DEQ, is handling that review process. And so, they're submitting their plans and they're going to review, but they have several years to put together those plans. So it's great, things are moving forward. The CEI hub.
I have one last question. So the earthquakes that were experienced in Turkey were sort of like this movement,
Yeah,
and the Cascadia subduction zone is going to be like this movement.
yeah.
So,
Yeah.
so are there things that we're going to experience that we're missing from this experience?
Yeah.
Or vice versa, or the things that they had that we won't have?
Yeah, that's a great question. So I'm gonna go all the way back. The big, I would say, difference, and it's actually not that different between these earthquakes, is that so these earthquakes with like these crustal faults, the duration, the magnitudes are lower, 7.8, 7.5. Subduction zone, we're designing, we're analyzing for a magnitude 9. So that's like over 10 times the amount of energy, right? Where our magnitudes are on a log scale. At least here in Portland, you can see that these areas were all very close to the fault, like we had near fault effects. Portland is, I think, almost like 100 kilometers away from the fault. But there's more energy, and as those waves are traveling, the paths can do different things. And then one of the big things is these earthquakes, they lasted for about 2 minutes, which is quite significant. That's a very long earthquake, and if you think about 2 minutes of shaking, that would feel like an eternity when you're experiencing it. With a magnitude 9 or a subduction zone earthquake, those will last longer. They're known to be long duration earthquakes. So I'm not sure what the estimates are, but it's like kind of 3, 4, 5 minutes of shaking that would take place in those earthquakes. Yeah.
Is it possible that all the flooding, you said it was most likely to settle in the area, and then
Seems that way, yeah.
is it possible that post liquefaction, those particles like reconsolidate, become more dense, or take it hard for water to seep through?
I think at the end of the day, it's still sand. Like it's, we think about permeabilities and like if you can pack sand, it's still pretty darn permeable. And we think about permeabilities on orders of magnitude, and you're probably at most getting like an order of magnitude difference, but it's still pretty permeable. So I don't know that that's quite, So Patrick, who I went to Turkey with, he has been doing some analysis since then, looking at INSAR data to look at settlement that has happened both pre-earthquake and since the earthquake. And you can see in that, it's like when you look at a map of the region, the area of Iskenderun is red, and the points in Iskenderun are red, showing that there's been regional subsidence ongoing in Iskenderun before the earthquake, and also that it's accelerated since. So it seems like just that subsidence. It's a sedimentary basin, so it's like thinking about geology, sediments get deposited and they weigh themselves down, and they're just settling over time, and more sediments come in and replenish, and so it seems we're just seeing geology happening.
All right, so we have time for one more question, and it's an online question.
Great. So just wondering, is there a way to use computers to recreate the infrastructure conditions prior to the earthquake to see how close the modeling comes to the actual results?
Oh, as far as like areas of damage, and I believe that there are efforts to do that using like open maps, which I'm sure you all in transportation are much more familiar with GIS and all those repositories than I am. And I believe so. With given building information, you can build up those models to create those. Create that.
All right, fantastic. Thanks, Diane, again. That was a great presentation. And then thank all of you for attending today's PSU transportation seminar in person and online. After the seminar ends, you'll have the opportunity to complete a brief survey about today's event. It only takes a few minutes and we would really appreciate your feedback, so please take that survey. Again, Diane, thank you so much, and thank all of you for joining us.